Welcome everyone to another episode of Mechanisms and Mentorship with your host, Rafael Testai. Today's special guest is Ben Sandoval. And today, Ben, let's just dive right in. People want to know, what's the problem that you were trying to solve? If you could just give us the big picture, if you were like explaining it to like a 10-year-old to just understand it, what would you say?
Well, a 10-year-old, that would be a little bit tough. But the two problems here, are actually three, that I was trying to solve were one, how to take a repeatable and non-contact measurements on a semi-rigid medical device shank. Two, a method to read or calculate the friction coefficients for nonlinear geometries. And design and build, program, and deliver those fixtures with a short lead time.
So let's talk about the first one. Could you repeat the first one again?
Develop a method for taking repeatable non-contact measurements on a semi-rigid, or in other words, flexible medical device shank.
Repeatable non-contact measurements. What's an example of that everyone can understand or have seen at home in their daily lives?
So a repeatable measuring system is one where you can take the same device and position it as such that every time you take a measurement, it is nearly the same, if not identical. So there are different levels of repeatability, but we strive to make things within the customer requirements.
Repeatable non-contact measurements.
By non-contact, those are measurements that you're taking without touching the device. So for instance, a laser line scanner is a non-contact measurement, or a picture in some ways is a non-contact measurement.
All right. And let's talk about the problem number 2 that you listed. Let's dive into that.
Developing a method for reading work and friction coefficients in nonlinear geometries.
I don't quite understand what that means. How could you break that down to be a little more digestible?
From the customer standpoint, they need to know that their device and how they're developing it is going to perform as advertised. So one of these devices is what's called a catheter. So it goes intravenously into the patient's body. Due to that, it can cause friction with the inner walls of the arteries. So we set up systems to measure that friction and make sure that the coating on the device is not causing any problems.
So there's a catheter going into the veins. We don't want to perforate the veins. So what kind of testing or coding do we need to do so that that doesn't happen?
One test that we do is what's called an insertion force test. And we can set speeds and forces and take measurements on that friction coefficient along its path of travel. So from that, you can either optimize or set boundary limits for how the device should perform, and then you can catch low-performing devices and quality problems down the line.
Okay. And what was number 3 that you listed?
So 3, this is an interesting one. Both of these fixtures had to be designed, procured, and assembled, then programmed, and delivered with a very short lead time. So these are very compressed delivery schedules.
So in the medical device industry, schedule is king. Is that fair to say?
That's very true.
All right. So that's the big picture problem that we're trying to solve, some of the constraints, and we deliver successfully. But let's talk about, how does a senior designer like yourself approach a design problem? Do you have a specific process you follow? If you could break that process down for us, maybe on the whiteboard or maybe just by talking about it, that would be splendid. So many of us are visual learners. Just go ahead and take it away.
So I was thinking about this question, and my answer is a bit of a mouthful, but I'll try and crank through it as fast as possible. it's a detailed process, and every designer has their own method that they follow, but Pipeline has some guiding principles and best practices and a design methodology that allows
Pipeline
us to do
is the
that.
company where Ben works at, by the way, just for clarification. Please keep going, yeah.
Yeah. Okay. So yeah, I follow that process, and it's flexible enough to allow for rapid development and prototyping, but constrained enough to make sure that I create a working and validated product every time.
All right.
So there's also a series of questions that come into play, which I think are the most important part for this project. So when I'm setting up these meetings and we have lots of design reviews with customers depending on the project, it's really important to establish what they're trying to accomplish. And it might sound crazy, but I say that because sometimes they come to us not knowing exactly what metrics they should be taking. And we're professionals in the medical device fixturing and equipment industry, so we can provide a lot of feedback based on that question. As well, we kind of dive into what are their lab capabilities. Is it an engineering team hiring us, or is it an engineering manager hiring us? Do they want all the details, or do they just want us to fix the problem, is what that tells us. I ask about...
So an engineering team wants all the details, but a manager just wants to solve the problem. Is that right?
For the most part,
Okay.
yeah. And there's always different mixtures of teams, and so having everybody around all the time isn't always beneficial, but having everybody around at some time is, because then you can get everybody's perspective and properly solve the problem for everybody.
Makes sense. How do you talk to a customer that thinks that they know what they want to measure, but after you take a look and Pipeline takes a look at the problem that they have in hand, you realize there are other metrics that in fact they should be tracking? How do you communicate to the customer in an elegant way?
That's a tough question, and usually the customer is king, right? If they want to take that metric and they are sure about it, I tend to not question too much. If I have insights and data-driven or past experiences that would allow me to clarify why it may make sense to take a different route, I just present those in a logical fashion. I don't get my heart set on it, though, because I want to make sure that the customer gets what they want, right?
Absolutely. All right, so part of the design process is really understanding the problem that the customers bring in, understanding who the customer is. What else is part of your design process?
So a big thing is getting more into the hard requirements of the machine, and that's, questions like, what are the environmental conditions? Are there specific sensor systems, controls, automation, safety, or UI, user interface type requirements? Do they want to be able to press buttons and change parameters, or do they just want tactile type buttons where they just push it and it starts?
Now, does the customer give you all these requirements up front, or do you have to dig for them and ask for them?
Asking for them is a bit of an art, and it can be a double-edged sword at some point. I want to make sure that I answer every question, and with the design, right? The design is almost a response to all of their questions. But it can very easily happen where you ask too many and you end up with too many design requirements, and it becomes more and more difficult. So at some point you start to lock down those designs, and the customer signs off on your design direction, and then you stick to it and try not to ask any more questions.
How do you ever get that feeling that, okay, it's maybe time to stop asking so many questions because these requirements are just piling up too much? How do you know that when it's time to just stop and get to work?
That's tough. I usually don't cut off questions completely. However, there is a time after, say, some proof of concept testing and 3D printed prototypes or basic programs where I've validated that the design I'm going to carry to the finish line is going to solve the problem. And at that point, once we've established that direction, there's not much of a need to keep going back and forth unless the customer has some additional requirements that they want sneak in towards the end. And we allow that, sometimes with process, and sometimes it's simpler than others.
So the great thing about a conversation is that it's fluid. And I want to ask you, what if when the customer signs off on the PO, the purchase order, everyone agrees basically on the hours and the budget of the whole project, but then the customer like starts asking to do add-ons that are out of scope and they're not free. So how do you bring it up to the customer in an elegant way?
Great thing to bring up. It happens with every customer. When they see capabilities towards the end, they start saying, "Oh, wait, this would be great. Can you throw this in there?" And if I can sneak it in a time efficient manner, I'll do my best. But for the most part, I have to go through due process and say, "Okay, you're changing the scope up too much. It's gonna cost more than we projected," and we just go through a formal scope creep or increase process and make sure that we take care of their needs.
But wasn't there a phrase maybe that when a customer asks for a new feature or something outside of scope, you say, well, how should we add that to the budget? Or wasn't there like a good comeback phrase?
Scope creep is what they call it, where your scope of the project is creeping outside of its boundaries.
Yeah, that's the term. That's what it's called. Like we have scope creep, but we don't tell the customer like this is scope creep. How much pay? Like it's something. I remember you saying this in a call that we have these daily huddles here at Pipeline that we all share what we're gonna do for the day, and it was like a very elegant comeback that you had. And I remember a long time ago that it was something like, "How would you like for us to build this time?" I think it was something like that.
Oh yeah. I don't know. You just have to be sure that they're aware that they're requesting things that are out of scope, and we keep good documentation to avoid that.
Okay.
But being specific about what problem we're solving from an engineering standpoint, what type of time budget up front is important, because then we can draw some lines if things are way outside of what we expected. And we're very flexible. That's almost to a fault, right? We really strive to hit all those points, and some of us engineers would rather fix the problem than submit an engineering change request or scope creep form, so we do our best to stay within the rules, but when it gets out of hand, you kind of know.
Absolutely. Let's see. So we've answered those questions. Let's talk about this particular design problem that we mentioned in the beginning. How did you go about solving this specific problem? And if you want to reference some of the CAD, some of the things that went through your mind.
Yeah, this one was interesting. So in solving these problems, I kind of mentioned, how do you want it packaged? What type of controls do you want? I also like to research the existing technology. Because usually in our industry, there are a lot of different customers that are trying to solve the same thing or have successfully solved the same thing in some way or another. So it's important to look at what's called state-of-the-art or existing technology that's in use. And that gives a lot of great insight. From an engineering standpoint. Obviously, we can't just straight up copy things, or, there's patents and things that we have to look out for. However, some things are not under patent, or some methods are well known and therefore not protected. And we can utilize some of those systems and solutions in our, chosen design path to meet the requirements.
I have a follow-up on that. I think the term is, how do you design around a patent? Is that what it's called? Designing around the patent?
Yeah, that's an interesting question. First, you need a patent lawyer, usually. Maybe, unless you're, well-versed in reading patents. And what the patent lawyer will do is he will go over the patent with you or by himself, and they are very good at indicating language and areas where you can change the design such that it doesn't defy any patents or copyright law type things. And then you file a patent for your new design, and you see if it plays out.
I think I used the wrong term. That's the correct answer to the question that I asked. More likely is when you're looking at the state-of-the-art solutions, how do you know how much you can copy from the state-of-the-art solutions versus make your own so it's not too similar? How do you find that area?
It's usually like if a customer is coming to us, there's not too much we have to worry about, because if that was the correct solution, we would recommend that for them, and they would probably cancel the project and purchase that piece of equipment. For the most part, unless we were going to mass produce it, we're not too worried about, patents and copyrights, because it's custom equipment. Everything that we make, we drop, and we usually do small quantities. So I'm never really too concerned with it, other than blatantly copying an existing technology. And I gave an example. This is what's called an IDTE machine built by MSI. It was one of the first machines that I looked at. It is very similar in purpose. It's made to test the performance characteristics of a medical device, under various, conditions: wet, dry, slippery, non-slippery turns. The mechanism that I was sort of interested in. So this is one of the machines that I took a look at, studied its function and its process. I didn't want to emulate it exactly, and the customer had some different parameters for me. So I took what I could learn from the way it's built and how they're engaging some things, and then I created a version of my own that hopefully improves usability and device installation, and from a software standpoint, the programming of the fixture. And
before we get into that, like what exactly it is that we're looking at, because I see a cable. If you want to replay it again, there's a cable going through what appears to be a roller mechanism, and I'm not sure what's happening. Ben mentioned something about friction. So could you point to us maybe with your mouse or your finger what's happening here?
So this is an intravenous catheter.
All right.
And what they're doing right now is either doing some cycling or some force testing by inserting this surgical device through a pathway.
Okay.
And then measuring either the wear and tear based on cycling or what kind of forces they're seeing after those cycles, and overall performance. So there's a number of different tests that they can take or perform with just this fixture, but one of the primary ones is force and durability over time.
All right, so here we see some wheels, some rollers. What appears to be happening over there?
So this medical device is being pushed through a pathway. They can be taking a number of measurements, whether it's force or torque, and get some data on how that device might perform in the real world, and more importantly, repeatable data from device to device, which allows them to find differences in performance based on small things such as like a coating or different bars and rings.
Okay. So to my understanding, the big picture is the medical device industry wants to do the best it can, so when it launches its products to the marketplace, nobody gets hurt. They're reliable, predictable, and they're the same product every single time that you buy it off the shelf. Is that right?
Correct.
All right, repeatability, perfect. So your inspiration here came exactly from where in this whole thing that's happening?
Well, that's just it. I mean, inspiration is a strong word in this case, but I was able to get a good look at how they're doing it. I was able to look at one of the machines and talk with an engineer that had been using it. One of our customers owns one, and they were able to go through with me some challenges that they have. Right? What's hard to use about the machine? What's difficult? What makes it not repeatable? And quite a few things came up, and that gives me a great inspiration for design. It's not necessarily the existing equipment, but what can be improved upon for the customer in a similar piece of equipment.
Right on. So it sounds like the process is the customer comes up to the engineer with a problem, to pipeline, and the engineer that works on the problem, and you basically want to refine the problem, get some requirements. Then you want to look at the marketplace and see what already exists to achieve something similar. You want to talk to people that have been using the solution already, see what could be improved, and then you mix it all together and you come up with your own solution. Is that right?
Correct.
Beautiful. All right, so let's talk about the own solution that you came up with. Beautiful transition. In the way, as we pull that up, comment below if you've ever experienced scope creep as an engineer. I'm interested to hearing your stories. Comment here below on LinkedIn or on the blog itself. All right, so yeah, now you mix it all together and let's see what the solution you come up with, what it is.
Well, the first one here, and these are actually for a similar device, so that's why it's interesting. This is a non-contact based measuring device, so it uses
just to get an idea, like tell people how tall is this so we can visualize
this is roughly 6 feet tall.
All right, just to get an idea. And what is it again?
This stage is mounted on an actuator, and it can travel up and down to look at the shaft of a device. These are microscope cameras, so they're very high resolution.
All right, so everyone, this is a camera. So the cameras are looking at a vertical shaft that wouldn't be in the middle, but we've hidden the vertical shaft because we don't want to show the customer's product, right?
Correct.
Perfect. So imagine a shaft in the middle. Go ahead.
So yeah, I mean, there's a shaft that would be coming down here. These are HDMI screens, so you can put a back image on there, like a template, and then these are 4K 60 microscope cameras with a big image sensor. These lenses are a little bit underpowered, but you can always upgrade them, move the camera around, focus it to get down to, phenomenal levels of measurement. And then, right now we're using it for some basic, surface inspection and mainly, angle straightness.
Just for the sake, do you remember by any chance ballpark how much is each one of these cameras?
They're not terribly expensive, anywhere from $1,000 to $2,000. Some machine vision systems can be in the $10,000 range, or laser line scanners in the $15,000 to $20,000, and we'll do all of that. This was actually considered more of a budget fixture because it's a fast timeline, so we have to use 3D printing for the majority of these components. Actually, everything you see here was designed and 3D printed.
Before we get into that, why don't you talk to us about the HDMI screens? Why do we want a screen behind that for?
So what it does is it gives you the ability to cast light or shadow and then compare with like a template. So you could project a screen on here that has different lines on it that tell you go or no go, or that the lines could tell you the angle that the device is at or its deviation from the norm. Okay. And that's just a flexibility we afforded the customer. And in some cases, you could just make it a white light, and then you have a very nice backdrop to take measurements off.
Now, the device is a cylinder, you said, right? Going through the middle of this. How is the device constrained? Are you using gravity for that?
So this is a rotational ring here, so you can actually turn the device
if you want to zoom in a little bit more
in a circle.
Yeah. Okay, but is the device hanging or is constrained by support?
The device is hanging.
Hanging. And why did you decide to have the device hang?
The customer wanted it to be gravity held, right? They wanted to hang it really straight and perpendicular, and then let it fall due to gravity. So there's actually a bit of a leveling process with this. And then we come down with that camera because it's on a linear axis, and we can watch it on the screen. And if it, veers left or right, we know, and we can even take a measurement of those deviations in the X and Y plane. And if you spin it around, you can find absolutes. But for the most part, this camera is giving you, say, an X deviation, and this camera's giving you a Y. So between those
Top
two,
view.
you can get a three-dimensional number on how deflected a device is at, 1 meter or 1.2 meters.
So we're testing for the device deflection. We want it to be perfectly straight. Is that right?
Hmm.
Why not put it on a table, perfectly straight, and then take the measurement orthogonal?
Well, as mentioned, it's a flexible shaft. So if you put it straight on a table,
The gravity.
it could bow one way or the other, for one, and it's very left up to the user, and with the gravity, there's a bit of gravity is helping pull it straight, and so we're concerned about how much of it is being pulled off to the side, right? Like, how off is it in its natural state?
So imagine it's hanging like a pendulum, basically, right?
Mm-hmm.
But wouldn't it be hard to measure because we're here in Phoenix, in Arizona, and it's quite hot, so there's air conditioning in the room. Any kind of vent can move this device, right? So how do you work with that?
Very true. You just don't put it next to a vent.
All right, so air can ruin the testing. So
It's funny you think of that, because I bring that up a lot, because some of these, even force sensors, can detect when the AC kicks on. And I tell people and they roll their eyes, but it's a true thing, like environmental stuff really can affect your test, especially for low pressure applications. That's when it drives the programmer nuts.
all right, perfect. Anything else that we want to say about this fixture?
That's about it. It was a fun one. I delivered this one at the end of January, I believe. And so far, so good. I believe. I probably need to follow up on it, but it served their purpose.
How did you get the idea to have this screen and the camera? So this is all gonna tie it into the first thing that he said, that we wanted to collect, if I believe, measurements in a non-contact way. Is that right? So this is the solution. I'm tying it all together. All right, so for the final part of this interview, we're going to talk about, as we know, is mechanisms and mentorship. So this is a mechanism that Ben designed, and if you could explain us, like, big picture, what the mechanism is supposed to do, and at the end you can talk to us about how you actually design it, some of the sketches, and what was going through your mind as you put it all together. Big picture, what does it do?
So what this does is it's similar to that mechanism that we saw, with some optimizations for very small medical device shafts. It basically grips a round shaft in between these pulleys, and they have a little indent in them.
In between the pulleys, so
right this way, right through there.
okay, right through there. I see it.
So
We have to hide the
basically-
medical device on purpose from the customer. We can only show the solution. So take it away. Go ahead.
So basically what you do is you clamp these, and they're adjustable in case you need to adjust just the center. And it gives you a very tight grip because these are a specific rubber coating. So you can take a very small shaft that might be impossible to grip with your fingers or, with conventional means, and put some serious clamping force on it without damaging the exterior. And then
How do you not damage the exterior, though, if you're putting significant force on it?
Well, in some cases we're pushing against like a stainless steel. So if we have a very soft material, as long as we're not over clamping it, then we're okay. And in this case, I have some hard stops and things, and the user can set the clamp force manually.
So as you can see, this black block on the right is the one that translates left and right, and that translation is actuated by the handle. Is that right?
Correct.
Okay. Can you lock the handle in place or no?
Not currently.
Okay.
Flexible. It was at one time, but it starts to get a little heavy.
I see. So you get it close, you squeeze the cable that's going in through. It's like the catheter cable.
Yep.
And why do you want to squeeze it?
Because we're going to drive that catheter into a small tube that has, a friction coating or a specific surface, and we're trying to take measurements on the force needed to pass that catheter through those those paths.
So if you do the normal to view from the side again, that had that small orifice that we were looking at just a few moments ago, what's going in
right here,
as you can see where the mouse is placed. What goes in through that is the catheter cable. Is that right?
uh-huh,
Okay. And on the other side, somewhere that's not on the screen, is going to be a receiving end that we're going to put the catheter cable through into, right?
correct.
All right. And we want to test the friction on that, how much force it takes to get through inside of it.
Exactly, and I can give you a better picture of what that looks like.
So check this out. Now we have the massive TLA, top level assembly, right?
So what we do here is we have some,
Ben.
like a carriage. Oh, sorry about that.
It's all,
We have a carriage here, and you mount your medical device. And there is here's the clamp that we saw. There's a potentiometer actually connected to this, so I can tell how deep the device is. And then there is a force sensor mounted on this side. Looks like it's hidden right now, but we're reading the force at this receiving end. This utilized what are called air bearings, so they're super low friction. And I have a little magnetic disconnect here because it's a very sensitive force sensor, so we don't want anybody like yanking on it or trying to screw stuff in. It is protected, but we take precautions like that. And the interesting thing that I didn't see coming is because of the way this thing is set up, when you flick the magnet, it's such low friction on the rails here that this whole assembly from this end, which is our little hose.
just make sure you follow the mouse when you're watching this.
Oh yeah, I almost need like a mouse pointer. From this end to this end, due to some tiny little magnetic forces and zero friction, will sit there and oscillate for a while between the magnets when you decouple it, which is a good little test to ask yourself, okay, well, how much friction are we getting? It's definitely, in the range of 10% of what a ball bearing might give you. So it's an extremely low friction coefficient when you throw in air rails, which translates to a very accurate and responsive reading on the force gauge. Yeah, and here's a quick video of just the software, and it can kind of show you.
So Ben also writes, you do software, is that correct?
I do.
The whole
correct.
package here.
So here's actually the device in motion. And yeah,
Beautiful.
And there's a little device holder as it's running down that carriage. And we also had a degree of twist in there. So what the software does here is it's plotting the position versus the force, and that's why it's making a little loop, because it showed the force going there and the force going back.
How big is this?
It has, it's roughly 8 feet. It has 2,000 unique parts. A lot of them are fasteners and hardware. But I think it actually has somewhere in the range of 70 to 80 custom parts and assemblies. And, so those are some pretty crunched design schedules. I mean, it's like modeling a few parts every day, 3D printing a few parts every day, procuring a few parts every day of that process, right? Like your whole fixture is toleranced off of that shaft axis. And
I think that's a golden nugget for people to take home and remember that. Any last words for any mechanical design engineers that may be watching this? Maybe some students in college or somebody early on in their career that you think that they should take this piece of advice from you?
With this fixture especially, and into newer fixtures, I really like to hammer out my best guess of what it's going to look like early and build a working prototype. And these are months before the fixture's due. I have something that's working and representative of the model, and then I do it again. And then I do it again. And then finally, when I feel like I've optimized everything I can, I procure the final components. So I guess my advice, for people doing this is to try again early on and learn everything you can before the machine needs to be built, so that by the time you get there, you've ironed out anything that might hold you back. It's a scary day when you have to build a machine and deliver it in a short timeline, because there are usually, in some cases, depending on how you design. Some things that need further rework or GD&T or, optimization. So getting that done early really just, by the time you build it, everything works. And that's a great feeling.
What if when you get the PO, there's really no time for that? It's like, you got to go in, dive in and start solving this, but you want to do what you just proposed. How do you squeeze that in?
Well, the fact of the matter is, for the most part, if you are ironing out these problems early on in the process, it's going to save you more hours than it costs in the end, because it takes a long time to do it correctly the second time as opposed to doing it correctly the first time. Like building the machine in its entirety the first time, if you do it correctly then, it's much faster than starting your prototyping process after the build. And that's why we prototype it early, so that by the time we get all the CNC machine shops to spin up their end mills and turn us parts, they're the right part. And everything fits together.
Well, thank you so much for being on this episode of Mentorship and Mechanisms, Ben. I really appreciate it. To follow Ben on LinkedIn, you find his link below for his LinkedIn account.
Haven't signed on in 2 years.
But he'll be there. Then pipeline design and engineering is where Ben works at, and they've developed all these fixtures. And to know more about these episodes that we'll be launching here at SOLIDWORKS, make sure you follow me on LinkedIn, Rafael Testai. Until next time.